So, hi everyone. This is the second part of the reference model for real-time system. Second and the last part. So here we will recap first what we have seen in the first lecture. It has we saw what is a processor and what is a resource. Processor typically means active resources. And resource means passive resources. We differentiated between job and task. So task consists of set of jobs. And the properties of these jobs like temporal parameters, functional parameters, resource parameters, and interconnection parameters we have seen. Then we saw what is release time, whether it has a fixed release time, or there's a jitter associated with, and whether it's a sporadic task or job. Execution time, we have seen minimum execution time, maximum execution time, and in a deterministic system, of course, always the maximum execution time is taken as execution time. So there is period P with respect to a periodic task and phase phi, and we saw what is hyper period, and you have a set of tasks. Hyper period is least common multiple of the periods of all the tasks. Then we saw a periodic and sporadic task. Now coming to the precedence constraints and data dependency among tasks or jobs. In a real-time system, there will be a set of tasks. There may be dependencies among tasks or jobs within the same task or within different tasks. So jobs will be there in different tasks, and there may be dependency across tasks within the same task. So here, jobs have precedent constraints. They can execute only in some order. If they have precedence constraints, if they can execute only in some order. If jobs of a task can execute in any order, they are independent. Precedence relation is denoted by partial order relation less simple less than. So partial order will be knowing it's reflective, anti-symmetric, and transitive. And we can refer the one of the online material for noting down what is partial relation, not partial order relation. So job Jx is producer of job Jy if Jy can execute only after Jx completes its execution. That is denoted by Jx less than Jy. When if Jx is less than Jy, never Jy can be less than Jx in a partial order. There is also this term immediate predecessor, successor, and immediate successor. Like successor of Jx is Jy. One of the successor, if it is immediate, means there is no other jobs between Jx and Jy. That is what is by immediate. It's a way to represent precedence constraints among jobs in a set J by a directed graph G. You have jobs and the relationship represented as a directed graph. So vertices in the graph represents a job. Could be a job Ji. H Jx Jy denotes like Jx is an immediate predecessor of Jy or Jy is an immediate successor of Jx respectively. So Jx is immediate predecessor of Jy and Jy is immediate successor of Jx. Both are correct. This graph is called precedence graph, where you have precedence relation shown between jobs. It could be even multiple tasks. A task graph gives us a general way to describe the application of the system. A task graph, when you have tasks, it will be an extension of the precedence graph, and the dependency could be across tasks. So we will see a detailed example on this. It's exactly what is there in the textbook. So task graph, an example we will see. Here we have first a job which has a release time of 0 and a deadline of 7. Deadline is relative deadline. So when it's released at 0, it should finish by 7. Next next job of the task comes at time 2, and the deadline is this absolute deadline, not relative deadline. Absolute deadline is 9. So it should, when it is released at 2, it should finish by 9. Then next is 4:11. Next is 6:30. It keeps on going. So 8:15. From this we can understand that every job, the period with the job is 2. First release at 0, then at 2, the difference is 2, then 4. After 2 it's at 4, so the difference is again 2. After 4, 6. So it's like period is 2. And the deadline is 7. So the relative deadline is 7, and the absolute deadline is shown in the actual this closed interval. It starts with the open interval and finishes with the closed interval. So the relative deadline is 7 units. This is what about this first task. And there is no dependency among jobs. So as far as job is released, it can execute immediately because the first job does not depend on second job. If there is a dependent, there will be a directed edge. It shows that there is a dependent. So all tasks are independent, so they can execute. All jobs in the task are independent, so it can execute when it is released. We are confusing between job and task. Please note that a job consists of multiple tasks. Sorry, a task consists of multiple jobs. So this is one task with 5 jobs shown, can keep on coming periodically. So one task and 5 jobs. So task consists of multiple jobs. Task consists of multiple jobs. This is the second task. Here it is released as time 2, and the deadline is 5. These are absolute time. So if you look at here, this has a phase of 2. Instead of starting at 0, first job is released at time 2. So phase is 2. 2 minus 0. First task and job of the first job of the first task was released at 0. So phase was 0. Here phase is 2. And the absolute deadline is 5, means the relative deadline is 3. 5 minus 2. Similarly, the second job of the task is released at 5, and the deadline is 8. Third one is released at 8, and deadline is 11. So you can find that the relative deadline is 3, and the period is also 3. After 2 at 5, after 5 is at 8, and after 8 is at 11, and after 11 is at 14. Also the relative deadline is 3. 17 minus 14, 14 minus 11, 11 minus 8, all are 3. So here, but there is a edge showing that the second job can start executing only after first job finishes. So the same task T2, the first we saw task 1 where there is no dependency. Second task, there is a dependency among jobs. So a job, second job can start only after first job finishes. Third can start only after first and second finishes. The first condition, like job J2 can finish only after J1, guarantees that J2 finishes, then J3 can start. So this is a periodic, these are two periodic tasks, one with dependence, one without dependence. The second job, there are two other things. There is a phase, that is 2 units, because first job is listed time equal to 2, and the period and deadline are the period and relative deadline are same. Now we'll see tasks which are not periodic, but there could be dependency. So here you have tasks, and you could see some different type of edges, a different type of nodes. So this is a conditional edge, denoting with hyphen, not a direct edge, and this is a join vertex. So we see what these are like. There's a precedence here, so every job is dependent on other job. Like J2 can start only after J1. Look at the values 0, 5, 4, 8, 5, 20. So they does not denote a period, and this one denote there is a periodic. They are periodic, but the phase is 0. These are all associated with the same task. Let this be task 3. Then you have another task. Again, phase is 0, then first task only the release time and the deadline is shown. Then here we have a rectangle now coming in. It's not rectangle, it's square actually. It should be square. If you feel like rectangle, it's square. So I am showing the entire graph. So here, what is the thing is there's a dependency between tasks. So here, this task may mm, uh, need the fourth task job J depends on third task second job to finish. So there are multiple predecessors for J. Look at the number of predecessors. Three predecessors are there, and for this J to start execution, all the three predecessors should complete execution. So that's what this J. But if you look at this square edge, that is this square edge, it has three predecessors. Like among these three, all are predecessors. But among the three predecessors, if two finishes, it can start execution. That's what this is shown as a square. Where among all the predecessors, only a subset of that predecessors need to finish, then it can execute. The proper subset. So proper subset means if the set size is say x, the number of jobs to finish is less than x. It would be 1 to x minus 1. And if you look at this square, there are two predecessors out of which one finishes, it can execute. What about this conditional block is there could be some condition based on which one of the path will be taken. So based on that, a job out of these two jobs, only one can actually execute. Both cannot execute. From here, there is a divergence. If suppose the condition then goes this direction, then this condition block. Finally, both joins at this point. Like this task takes a deviation, or so it's like a condition joining. Like either from here it should go in this way direction, like the same task in this direction, or it should go to the third task job, sorry, fourth task job like this, and then join again here. This join node where you have paths from two different nodes merging. That's a conditional block also here, like edge. It's also shown as a conditional edge, but there could be alternative paths. So why there's alternative path here is like here and in this direction. So what you have to remember is from these values is this is a periodic task, this is also periodic task. So first two tasks are periodic, second task has a phase of 2, second task period is 3, deadline is 3, relative deadline is 3. This task phase is 0, relative deadline is 7, period is 2. So even if the before the first job finishes, second job is released and it can start executing. Like first job starts at 0, suppose it is finishes by time 5. By the time second job is also released, can also start executing if you have multiple computing units. So it's not necessary that first job should finish, then only the second job should be released. But here, if jobs are released, still the precedence relation should be maintained. So J2 cannot start executing unless J1 is finished in the second periodic task. This below diagram is not a periodic task, but it shows the conditional block which where there can be divergence in path out of which only one can take. Then it leads to a join node. In this square node where there are multiple predecessors, but if among the x number of predecessors, 1 to x minus 1, a subset of predecessors finishes, it can start executing. But in this job J, all the predecessors should finish, then only it can start executing. This is about task graph, an example we have seen. So you got an idea about what is jobs in a task, what is periodic task, what is phase, how jobs are released and how jobs can execute. So you found in the first task that before job 1 finishes, job 2 can start in the task 1. That is with this task. J1 can start and J2 can run. Both can run simultaneously if you have multi-core, multiple processing unit. So even before J1 is finished, J2 is released. That's possible. So here it may not be possible because look at the deadline and release time. So here for second task, release time of J2 is 5. By that time, first job should be finished. So there's a dependency. So J2 can execute only after J1. So this is not a periodic task model, but uh, we have shown condition blocks, join nodes, this square nodes, and you should understand the meaning of this. So temporal dependencies is like difference in completion time of two jobs is called temporal distance. Task graph represents this by temporal distance edges and or precedence constraint. A job with more than one immediate predecessor must wait until its immediate predecessor completed execution. It must wait until all its immediate predecessors are completed execution. It's called and it like I have shown here, like all the predecessors should complete. Like that. And sometimes a job can start execution if one or some of its immediate predecessors have completed execution. Or jobs, like these all jobs are represented by square vertices. Then conditional branches, like only one branch in each condition block is executed. Join nodes are associated with each branch. So here you have this condition block and the join node. Join nodes are typically shown by filled circles. That's about this small example. So few more points we'll discuss during live session. We can have interactive live session like this, like whether a job can be preempted, how important a job is, whether optional execution of a task or a job is possible, whether a resource can be preempted, what about resource graph, resources can be represented as a graph. So we have concluded the reference model for real-time system. Tuesday we'll meet on live session and during that time we'll clear the doubts and then we'll move to the next part, that is scheduling algorithms. So by this time you should have watched all these lectures and then clear the doubts, and based on that we can move forward. So that's about reference model, and next topic is on scheduling. Okay, so in stopping.